A synaptic matrix model can be used to visualize the hypothesis that memory is stored as the strengths of synaptic connections in neural circuits. Imagine we have 5 output neurons, here labeled with Roman numerals 1 through 5, whose dendrites intersect with and can receive input from 5 axons, here labeled with letters A through E. A subset of these intersections results in the formation of synapses, as represented by the dots. We can simplify the model by using 1 to represent sites with synaptic connections and 0 to represent sites without synaptic connections. The firing patterns of the presynaptic axons A through E provide input into the system. 1 represents the firing of an input neuron, and 0 represents no firing at a given time. In this matrix, the firing threshold of each postsynaptic output neuron follows the integration rule that if 2 or more of its presynaptic partners are firing simultaneously, it will fire its own action potential. The input-output pattern of this circuit can, in principle, be used as a model for event-triggered memory recall, where each input pattern represents an event, and each output pattern represents a memory of the event. This 5x5 matrix has 2 to the 5 times 5, or 2 to the 25th, or 30 million possible binary codes. A 100 by 100 matrix has 2 to the 100 times 100, or 2 to the 10,000 possible codes, a value that exceeds the total number of atoms in the universe. And while this seems like a very big number, neural circuits are not binary. In reality, synaptic weight can be any weight between 0, no connection, and 1, a maximum strength connection. Thus, synaptic weight matrices can, in principle, store enormous amounts of information that can be used to transform specific input patterns, or events, to specific output patterns, or memory recalls. The value of synaptic weight matrices can also be adjusted by learning, which can produce different outputs in response to the same input. In the fruit fly, each odor-specific neuron activates a specific set of glomeruli. This information is relayed by a specific set of olfactory projection neurons that activate a specific set of higher-order mushroom body neurons. The information is then relayed through mushroom body axons to mushroom body output neurons. This, in effect, creates a synaptic matrix. As shown by experimentation, the matrix is influenced by learning through the action of modulatory neurons. An output neuron that responds to aversive stimuli will not be activated by a neutral odor. When the odor is paired with an electric shock, the modulatory neuron activated by the shock modulates the connections between the mushroom body neuron and the aversive mushroom body output neuron. After training, subsequent stimulation with the neutral odor alone will now activate this output neuron. Likewise, the pairing of food and odor will alter the synaptic matrix of an attractive output neuron, such that after training, a neutral odor will activate the attractive neuron. The mushroom body circuit in Drosophila provides a specific example of how a synaptic weight matrix can be altered by learning, such that before and after learning, the same odor elicits different behavioral responses.